The science behind a PET scan. Hi, and welcome back. This video series will help you understand, step by step, how a PET scan works. Make sure to watch the videos in the correct order, as the information in each video builds upon the previous ones. Here you can see the journey we are on to understand the science behind a PET scan. Last time we talked about the atom. In this video we'll learn what happens when atoms are unstable and begin to decay. In the next video we'll continue with the synthesis of the radioactive tracer. And finally we'll look at the creation and analysis of the images. The other videos are linked in the description box down below. So if you've already seen this one or you've skipped a video, make sure to check out the others. Today we will learn about radioactive decay, which is the key characteristic of the radioactive tracer used in PET scans. First, we'll repeat some concepts from the last video. Then we'll look at what radioactive decay is, discuss the concept of half-lives, and finally we'll summarize the most important concepts. Let's repeat what we learned in the last video. Atoms are the basic building blocks of all matter. A nucleus is held together by the strong nuclear force. In order to remain stable, the nucleus will typically need at least as many neutrons as protons. We've heard the terms spontaneous rearrangement and radioactive decay a few times, but haven't yet gone into depths about what they mean and how they are linked together. Here is a definition from the Encyclopedia Britannica. An unstable nucleus will decompose spontaneously or decay into a more stable configuration, but will do so only in a few specific ways, by emitting certain particles or electromagnetic energy. So, an unstable nucleus becomes stable by emitting certain particles or electromagnetic energy. Let's take a closer look at that. It's important to note that an unstable nucleus doesn't imply that it will decay instantly. It is possible for a nucleus to remain unstable for only a few nanoseconds or even for billions of years. Radioactive decay happens in a random and spontaneous manner. There are three types of decay, namely alpha, beta, and gamma decay. During alpha and beta decay, which includes beta plus and beta minus decay, particles with mass are emitted. During gamma decay, gamma rays are emitted, which are light waves. We won't go further into depth about all the types of decay, as only beta plus decay is relevant for PET scans. The conservation of the total number of nucleons is a main part of radioactive decay, and we will talk about it in just a moment. Here is an example of the conservation of the total number of nucleons. In both circles, we have 7 particles in total. Before the decay, we had 5 protons and 2 neutrons. After the decay, we have 4 protons and 3 neutrons. Even though the number of protons and neutrons differs between the circles, both circles still have the same total number of particles. So, whenever an atom X decays into an atom Y, they will both always have the same total number of protons and neutrons. Now we can combine everything we've learned so far. During beta plus decay, a substance is unstable because it has too many protons. Because protons repel each other, there is a huge electrostatic repulsion. Due to not having enough neutrons in the nucleus, the strong nuclear force isn't able to balance out the electrostatic repulsion. In order to become stable, it undergoes radioactive decay. That means the nucleus transforms one of its excess protons into a neutron. The atom is conserving its number of nucleons when the proton is transformed into a neutron. That neutron is then able to increase the strong nuclear force and balance out the repulsion so that the atom is stable. Here is the beta plus decay pictured graphically. The darker circle represents an unstable atom X with A, number of particles in total, and Z, number of protons. It undergoes the process of beta plus decay and becomes atom Y, the lighter circle, by transforming its excess proton into a neutron. You can see this here because A, number of particles, has stayed the same, whilst Z, number of protons, has now decreased by 1. During the beta plus decay, a positron and a neutrino are emitted from the parent nucleus. The emitted positron is our main player for the PET scans, hence the name positron emission tomography. The half-life is defined as the time it takes for a certain mass of an isotope to become half of its initial amount by undergoing decay. Let's look at an example. Consider a radioactive isotope called fluorine-18. F-18 is one of the most frequently used isotopes for creating the radio tracers that are used in PET scans. Its half-life is 109 minutes, so almost 2 hours. That means every 109 minutes, F-18 will decay by half the amount it was before. If we start with 100 grams of F-18, after 109 minutes, we will only have 50 grams left. After another 109 minutes, we'll only have 25 grams left. And after another 109 minutes, we'll only have 12.5 grams left. I think you understand the concept. During the process of a PET scan, it is important for the doctors to know what the half-life of the radioactive substance is. It determines how long the tracer remains radioactive in the body. And it's a huge difference if the radioactive tracer is active in the body for only a second or for millions of years. Let's summarize. An unstable nucleus will eventually decay in order to become stable. The different forms of decay are alpha, beta, and gamma decay. The decay that is relevant for PET scans is beta plus decay. When a nucleus is unstable due to having an excess proton, it transforms that proton into a neutron by undergoing decay. At the same time, a positron and a neutrino are emitted. The positron is our main player here. Half-life is the time it takes for a certain mass of an isotope to become half of its initial amount. That determines how long the radio tracer stays active in the body. The next time you make your bed, try and talk yourself through the process of a beta plus decay. It will help you remember it. Thanks for tuning in, and see you soon!